All right, let's start lecture B by doing these two integrals as fast as we can here so we can get to the other stuff. The only difference in this next one is I put an x up top, but the same method will work, though the answer will be different. You can still factor the bottom as x plus 2 times x plus 3, and you can still set this equal to some a over x plus 2 plus some b over x plus 3. It does turn out that when you have linear factors in the bottoms of these things, that up top you only need constants. We will be able to solve for a and b. If we had irreducible quadratics on the bottom, an x squared that we term or expression that we cannot factor, then we have to allow for linear functions on the top. Ax plus b on the top of that fraction, for example. Once again, multiply both sides by x plus 2 times x plus 3. On the left, you're left with an x. On the right, you're left with a times x plus 3 plus b times x plus 2. Once again, you can expand things out to get a coefficient times x plus another coefficient that would be the constant term. In this case, the left side only involves the x term and no constant term, so the coefficient of x on the right would have to equal 1, and the constant term would have to equal 0, and you can just solve for a and b. But it's quicker to let x equal -3 and -2 and see what happens. When x is -3, or I guess I wrote -2 there, you get -2 on the left, you get a times 1 plus b times 0 on the right. In other words, a is -2. And when x is -3, -3 on the left, a times 0 plus b times -1. So that b is actually now +3. So this becomes -2 over x plus 2 plus 3 over x plus 3. And the integral is going to involve logarithms again. By the way, you can always double check this by going backwards. You can try to combine these fractions by getting a common denominator. You can always check it. In this case, it would look like this when you check it. Hopefully the top simplifies to x. -2x minus 6 plus 3x plus 6 on top. And the 6's cancel, and the 3x minus 2x is an x. It checks. I don't have to keep writing here. So this integral becomes, let's write it this way. That integral, which will be 3 natural log of the absolute value of x plus 3 minus 2 times the natural log of the absolute value of x plus 2 plus c. That can also be written as natural log of the absolute value of x plus 3 quantity cubed over x plus 2 quantity squared plus c. That's an okay way to write it as well. So I brought the 3 up there and the 2 up there, and then I combine the logarithms like before. The difference of 2 logs is the logarithm quotient. And again, the absolute value signs can go around the entire thing if you like, or each individual thing, it doesn't matter. This one's going to take a little bit longer, because before I can try to use partial fractions, when the numerator has the same degree or higher degree than the denominator, you should divide those polynomials first. Long division. Make your long division symbol. Put the numerator inside, that's the thing up top. Put the denominator outside here. It's a little strange, but this is the way to do it. Look at the highest powers. What should you multiply x squared by to get x squared? You should multiply it by 1. Put a 1 up there. Now multiply that 1 times each of these things and put them down here. And now subtract. This thing now has a lower degree than this thing does. The degree of that is 2, that's the highest power. The degree of this is 1. You can stop. You were done with your long division. The long division wasn't too long. What does it mean? That's more important. When you do long division or whatever, divide, for example, 73 divided by 4, for example. You don't really need long division to do that. I guess I will, just to show it to you. Put a 1 there, put a 4 there, subtract. 4 goes into 33 8 times. The 1 is your remainder. What does this mean? It means 73/4 is the same as 18 plus 1/4. 18 and 1/4. The quotient 18 goes there. The remainder goes over the original thing you were dividing by. 73/4 is 18 and 1/4. Same kind of idea here. What this means is the original fraction, x squared over x squared plus 5x plus 6, is the quotient 1 plus the remainder, negative 5x minus 6, over the original thing you were dividing by, x squared plus 5x plus 6. Integrating 1's easy. Integrating that involves partial fractions now. The numerator has a lower degree than the denominator. So we can now use partial fractions on that part. So this can be written as a over x plus 2 plus b over x plus 3 as well. Because that's how you can factor the bottom, is x plus 2 times x plus 3. When you multiply by that common denominator, you get negative 5x minus 6 equals a times x plus 3 plus b times x plus 2. Right? Tracking with me here? Solve for a and b. Use x equals negative 2 and negative 3 again. When x is negative 2 now, it's a little trickier. The left is, careful, 10 minus 6, 4. Right? Negative 5 times negative 2 is 10, minus 6 is 4. On the right, that goes away. This becomes a. A is 4. When x is negative 3, negative 5 times negative 3 is positive 15, minus 6 is positive 9. 9 equals, that goes away, that becomes a negative 1. You get negative b, so b is negative 9. Now we're ready to do the integral. Don't forget your 1 here. 1, a is positive, I guess I'll write that next, plus 4 over x plus 2 minus 9 over x plus 3. Catch me if I make a mistake here. I think we're okay. Each of those is easy to do. Leave the answer that way, or you can write it like this. Either way is okay. Okay, so again, whenever the rational function is such that the numerator has a degree equal to or higher than the denominator, you should do the long division first before you try using partial fractions. These, again, are the easiest cases. It gets harder when you got to deal with irreducible polynomials that can't be factored so nicely. Maybe not at all, at least in terms of real numbers. It also is harder when you've got something squared at the bottom to deal with. Okay, there are, maybe I shouldn't say harder, but you have to do modifications to get it to work out right in those cases. And sometimes you have to complete the square as well. All right, let's see. We have 17, 18 minutes left. So we've done our calculations related to chapter 7 for the day. Now let's learn about more parametric curve stuff. Let's quickly look at mathematical homework number 2. So once again, you can work in groups. You can work by yourself or in groups of 2 or 3. Put one person's name at the beginning of the file name. That person should probably be the one who puts it on rule. Put everybody's names in there. Don't forget anybody's names. Double check that before you turn it in. Let's go ahead and start to work on this as learning about parametric equations and curves as part of the lecture here for today. So look at exercise 1. The parametric equations, x equals cosine of 2 pi t and y equals sine of 2 pi t, as well as the point valued function where you put those in a point, and I'm calling that function c of t, model motion at a constant speed counterclockwise around the unit circle as t increases from 0 to 1. Use manipulate and parametric plot to make an animation showing this motion. Also use plot range, but this time we'll also make use of show and ListPlot to make a dot where the object is as we move. So, you learn about these things in the videos, but I will go ahead and show you what to do here now too. So we're first going to define f and g. Make this bigger. F of t is going to be cosine of 2 pi t. Built-in Mathematica functions are always capitalized, including cosine, sine, tangent. Function arguments always get square brackets. That's true for functions like manipulate and show and plot. Parametric plot is also true for mathematical functions like cosine, square brackets. 2 pi. The pi is in the palette here. If you look over here, which again you can get to by going to the palettes menu, you can find pi under typesetting here. Click on this tab right there. That's got symbols behind it. Pi is right where? Right down there. But it's quicker to either do capital PI, that stands for the number pi, or what's more fun is to do escape P escape, that makes a pi symbol. You might want to write that down. Escape P escape makes a pi symbol. Don't put a t next to the pi like that, because if you do, Mathematica will treat that as one variable, pi t. You don't want that. You want the t to be the only variable, so either put a space, or as a default, always put a star for multiplication. I don't need the star between the 2 and the pi, because those are just plain numbers. Mathematica knows to multiply them when they're right next to each other. But when you've got a variable in there, it's always a good habit to put a star. You can put a space, but it's easy to forget a space. So I, as a habit, always put a star for multiplication. And again, when you define functions first, you use the underscore after the variable name, and a colon equals. Once you define the functions, you don't need those things anymore. Semicolons suppress output, but I like using them to sort of just separate different equations and commands. C of t is a point. Don't use parentheses. Points in Mathematica are represented with curly braces, as what Mathematica calls lists. Lists have lots of applications, not just the points, but you can put the f of t and g of t inside the list with curly braces. You don't need underscores with the F and G, because they've already been defined. That enters the functions. Go ahead and hit Shift Return. They are entered in the memory now. You can use them. You can, for example, plug in pi over 4 into C and see what you get. That's what you get. It's because of the 2 pi in there. Get a pi squared. Let's try just 1/4 actually. Now it simplifies because 1/4 times 2 pi is pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. One-sixth times 2 pi is pi over 3. Cosine of pi over 3 is 1/2. Sine of pi over 3 is square root of 3 over 2. You don't have to enter that like I did. I was just doing that to illustrate. Okay, so now we want to do all the things it says to do using all these commands. It's always a good idea in Mathematica programming to start simple and make things more complicated as you make sure the simple things work first. So I don't think it's a bad idea to just do the parametric plot first. It's not your final answer. But just do that first. Capital P's in most spots. It's a built-in function. And when you've got a second word, that should be capitalized as well. As a habit, again, use square brackets for function arguments. Put both square brackets right away so you don't forget the second one. Because common mistakes are to forget square brackets or to forget curly braces or to forget commas. Those are the most common mistakes, and these are tricks to avoid those kind of mistakes. Parametric plot plots parametric curves. I could plug in f of t comma g of t inside curly braces as what I want to plot, but I've already defined c of t, I might as well use it. And c of t already has the curly braces in its definition, so I can just type c of t. Put a comma, and then inside a list you put the range of values for t. T goes from 0 to 1. Inside curly braces, put t comma 0 comma 1. This is a basic built-in command here that we can now use. This will produce a plot. Not the final answer, but a plot. There it is. Does it look like a circle to you guys? And it looks more like an oval. Why? Well, it's because the axes don't have the same scale. If you use aspect ratio, which I guess I didn't tell you you had to do, you can make the axes have the same scale. It's called an option, aspect ratio, capital A, capital R. And by the way, you can see the command it thinks you want coming up there. You could just click on that. Aspect ratio. As an option, it requires an arrow. Now, Mathematica put an arrow in there for me, but I could have typed the arrow as a minus sign, then a greater than sign, and as you continue typing, it merges into an arrow. Automatic is the thing to do to make the scales the same. Well, oftentimes it is. It still looks the same, doesn't it? It looks like an oval on my screen too. Sometimes automatic makes the scales the same, sometimes one makes them the same. And neither of them is working now. Wow. It does look oval on my screen, it looks oval on yours too. I don't know why it's not making it scales the same. The automatic almost always works as far as I know. All right, let's not worry about that for the moment then. Get rid of that. We want to make an animation with manipulate. And use plot range to keep the window fixed. Let's use the plot range in here first. Plot range. Plot range is an option as well, and you need an arrow after it. If you just put a single number, like 2, after plot range, it'll plot from -2 to -2 in both the x and y directions. Like that. In general, though, you might want to have different windows. in different x mins versus y mins and x maxes versus y maxes. So for example, this would be the syntax to plot in the window where x goes between -2 and 5 and y goes between -3 and 4. That's not the one I really want to use, but there we go. X goes between -2 and 5 and y goes between -3 and 4. Let's go back to doing something simpler. Like that. Notice I do keep re-entering this stuff, these commands. That's okay. I do get the output numbering continuing to go up. I'm to output 12 now. If I re-enter it again, I'll see output 13. That's okay to do. Manipulate makes the animation. I can put all this inside of manipulate. In other words, put a manipulate in front of it and put the square brackets around it. Now the parametric plot is inside the manipulate. You see a little red caret symbol there. That's to remind you you need more input for manipulate. And in the videos, I always end up doing something like this. B goes from 0.001 to 1 inside a list. As I have this right now, is it going to really do anything as B changes? No, it's not going to do anything as B changes because I don't have the B inside the parametric plot. B is my animation parameter, but nothing's going to happen as I slide the B because it's not affecting the parametric plot in any way. Remember, parametric plots are curves are more than just curves, they are modeling motion. We want to see the motion here. To see the motion, change your right endpoint to being a B. Then as B changes, that will continue to get updated. You'll see more and more of the parametric curve as B continues to increase. It is an animation. You're seeing different frames effectively for different values of B in rapid succession, giving you the illusion of motion. Now let B go, and there's your motion. It is supposed to be a circle. Does that look a little bit more like a circle? Looks like a circle, a little bit more at least. It is circular motion. That is the unit circle. We are tracing out the motion at constant speed. That's a constant speed motion. What if I want to do the other stuff? Get the dot in there with show and ListPlot. Show combines graphics. So I want everything inside the manipulate. So the manipulate is going to be the most outside thing here. Show is going to be the next most outside thing. So I put the show in and I put its end square bracket over here. And in fact, I think what I'll do is I'll put the ending square bracket of the parametric plot right here, so that this becomes the end square bracket of the show, so the plot range is outside the plot, because I'm going to want the same plot range for both the parametric plot and the list plot. I highlighted that square bracket, and that one gets highlighted at the same time to indicate that those go together. It's a quick way to see where your square brackets are matching up. I also want to put the list plot in here. I can either put it before or after the parametric plot. It doesn't matter in this case. List plot plots points as dots. If I just type C of B in here, it will plot that dot as B changes. You want C of B, not C of T, because you want the dot to move as B changes. T varies over an entire interval. You want the point to move as B changes, you need to put a B inside there. And sometimes it does this funny thing. Oops, I made a mistake. You need extra curly braces around the C of B, it turns out. And it doesn't put the origin where it should be for some reason, and slides the axes. That's annoying to me. I don't know why it does that. That can be fixed by adding an option, axes, origin, arrow, 0, 0, and curly braces. Then it will keep it where it should be. So now you see the dot, showing you the object where it is as time goes by. d is time. It's not the only exercise in this. If you watch the videos, you're also going to ultimately find a function that I call h of t that increases from 0 to 1 in such a way to make the motion model be an increasing speed rather than a decreasing speed. You'll see this h of t in the videos. What I'd like to do for just a couple more minutes here that we have left is I'd like to add a position vector to this picture. You're not required to do this for these exercises, but I ultimately do them in the videos, and they are important to talk about vectors and ultimately position vectors and velocity vectors to relate them to speed and distance traveled. We're not getting to the speed and distance traveled like I wanted to. That's okay. We'll do it next time. How can you add in some arrows to this picture, and in particular the position vector pointing from the origin to the dot as it moves? It's a bit tricky. Inside the show you need another graphics command, and in fact this graphics command is called graphics. How about that? Okay. You don't need to know this for this assignment, so you don't have to write this down. I'll show it to you again next time. If I, for example, want to make an arrow going from the origin to the point as it moves, this is the syntax. Graphics and arrow combine in that kind of way to make an arrow that goes from the origin, represented by 0, 0, to C of B, the point, as B changes. So we will see the position vector, the arrow, follow the point as it moves. The point moves, the position vector moves. Okay? So this is your first use of Mathematica in this course, beyond just basically doing integrals. And I think it's an important application. It's useful for physics, useful for multivariable calculus, useful for differential equations. Have a good day.